We're beginning tomorrow to study limits in regard to 1.2. Well, we have to think what we've accomplished. First of all, we looked at the discussion of evaluating limits from a picture, more or less show and tell. The next thing we're going to do is, using tables in the graphing calculator, see how the calculator performs as x gets closer and closer to whether it's c, or whether it's infinity, or whether it's negative infinity. Then we're going to use all of our proofs in the definition of limits, including the epsilon and delta proof, to do applied proofs in the definition of limits. Now, be not of weary heart, because the only ones I'm going to do with you are linear epsilon and delta proofs. So here it goes. Let's revisit the first problem, number 1 of 1.2, where we've taken the limit as x approaches 2 of x minus 2 over x squared minus x minus 2. Now remember, you did this problem by looking at a chart. Okay, now let's look at it algebraically. Always try to get several scopes. In an AP exam, you must look at the problem in terms of its graphic relationship, then look at it algebraically, and then basically look at it theoretically. Okay, as x approaches 2, the top would give you a 0. As x approaches 2, you see I'm trying substitution. The bottom would give you 0. So you have a form that's very, very special. It's one of the 6 special limits. And in the 6 special limits, the first one will tell you that the limit of f of x over g of x, this is a rational function, f of x and g of x, as x approach either c, infinity, or negative infinity. If it is of the form 0 over 0, you can do a magic trick. You can take, and you can't do it now because you're too young. You're not old and cute anymore. Of the derivative of f, which you do in chapter 2, and the derivative of g. And this will help you get an answer. This is called L'Hopital's rule. But my simple people, guess what? We're not there. You're still a babe. So, in your simplest sense, the only thing that you know how to do is to factor, because you're not smart enough yet. Now let's see what this will entail. What happens here is this cancel out. Uh-oh. Go to algebra 2. We think to ourselves, we have a removal discontinuity at x equal 2. Now we further think to ourselves, look how you're extending this. Not only do we have a removable discontinuity, I'll have an open circle on a graph of this. Now, does a calculator give me that? As x is 2, what would be the value of y? Well, if you look at this in reduced form after you cancel, you have 1 over x plus 1. So the y value would be 1/3. Now, this truly upholds the definition of limit. If you remember in the epsilon delta definition of limit, I deleted my c, I deleted my 2. But as the graph performed 1 over x plus 1, we get to a y value of 1/3. Now consider what it would look like. If you take your graphing calculator and you graph this, and here's a -1, when x is 2, the y value is very, very small. It's 1/3. So this would be the point at 2, 1/3. Okay, now let's extend all this. Take out your graphing calculator and graph that graph. There's lots of things that you're going to see. You're going to see through mathematical reasoning is if we have x going to infinity of this same problem, that this bottom would get bigger and bigger and bigger. So therefore your answer would be 0. This is the definition of a horizontal asymptote, which is the limit of f of x as x approaches infinity is L. So when you would graph this thing, you would have a horizontal asymptote at, and if I can get my pen to write, at y equals 0. What else do you understand about this graph? Well, this is what I'm talking about. We have a very, very simple problem faced, and I can tell my little child in here that to do this problem, all you really need to know is that substitution failed. You got 0 over 0. Yay, yay, yay. You can't do that because you're not old enough to know L'Hopital's rule to 2 weeks from now. So you just factor like you did when you were a child, and you get 1 over x plus 1. You put a 2 in there, you get a third. So when the domain is 2, the y value is a third, and you finished. The person that gets the A realizes that the A people are going to say, I have reduced f of x to g of x over 1 over x plus 1. As x approaches 2, my value is a third. At x equals -1, I have a vertical asymptote. So therefore, as x goes to infinity, the y value is 0. Then the A plus student will look at the problem and say to themselves, what is the limit of 1 over x plus 1 as x approaches -1 from the right side? Well, -1 on the right side is a number like -1.99999 all over, and we have a plus 1. So we'll have 1 over a positive little bit, so this limit is infinity. So this graph is going to come down here, and it's going to flatten out to y equals 0 as we go here. Now, it may go up and down y equals 0, but it's going to flatten out there. Then the A super plus person would then realize that as x approaches -1 from the left side, this number is like -1.01 plus 1. So you'd have 1 over a negative little bit, and therefore that would give us negative infinity. So on this side, as we approach -1, we're coming from negative infinity, and as x approaches negative infinity, it's going to flatten out to y equals 0 again. So to do the problem, you'll make the same grade as the thinker with the A double plus or triple plus person. But when we take free response questions, it will say, evaluate the limit of such a problem and discuss and check its graph. So all AP questions are higher order thinking questions and cover usually more than one chapter. There'll be 6 parts to every AP subjective question, which is worth 60% of your grade. Good stuff. Okay, let's have some more fun and change the page. Come on, change the page. Okay, so now it's time to go again to 1.2, and we look at a simple problem called rationalization. So let's say you're taking the limit, and we'll go to problem number 3, and you're taking the limit as x approaches 0 of the square root of x plus 3 minus radical 3 all over x. Okay, you substitute. You put an x as 0 here, you get a 0. You put a 0 in the top, you get 0 again. L'Hopital. Shortcut. Chapter 2, we're 2 done. So what are we going to do? We're going to go back to the old days of Algebra 1, and we're going to rationalize this crazy thing. Multiplying by the conjugate. Now, remember when you multiply the top out, it's in the form of a plus b, a minus b. but don't blend your terms in the bottom. Keep them separate. No. Interesting idea. Cancel, cancel. But this x cancels with the x here, leaving you 1 over this. So as x approaches 0, the limit of the function is 2 root 3. So you're really, truly not graphing the problem. What you were truly graphing is this reduction. That's what you were truly doing. And again, what does the graph look like? How does it behave as x approaches 0? Do we have a horizontal asymptote? It's obvious, since this factored out that x equals 0 was a removable discontinuity. Now, I'm piddling with you. I'm trying to boggle your mind. At the same time, I am thinking of all the things that you should have learned. Any questions? Think to yourself, direct them in class. Okay, now, together as we change the page, you had a day with me where I talked about special limits. And I did the proofs of those special limits, and by this time you have memorized them. Now, a very good friend is the limit as theta approaches 0 of the sine of theta over theta. And if you remember when we discussed that, I gave you the handout that was a 2-page proof of that theorem. This theorem can be proved in exactly 1 step, but not till you get smart and learn L'Hopital in chapter 2. Again, 2 weeks away. And this is equal to the same as theta over sine of theta, and this will equal 1. So you're going to have problems like this, and suppose a problem is worded, what is the limit as x approaches 0 of the sine of 5x over x? Now, look at this problem. Here's the angle theta, this is theta. This angle is 5x, this angle is x. X is not 5x. So what you do is fiddle. If you want this angle to match this angle, this has to match this. You fiddle. That means you create. So we're going to fiddle away, and we had an x. We want it to be 5x, so we multiplied by 5 over 5, which is 1. So if you look at it long and hard enough, your true problem basically is 5 times the sine of 5x over 5x. This is the angle, this is the angle. Life is sweet. This is 1. Your answer is 5. Cute. Suppose you have a problem. Come on, baby. Change pages. It has a personality. It doesn't want to change pages. Suppose we have the problem is the limit as x approaches 0 of 1 minus the cosine of x, quantity squared over x. Well, you're smart enough to remember that I gave you as a limit as theta approaches 0 of 1 minus the cosine of theta over theta had the same limit as the limit as theta approaches 0 of the cosine of theta minus 1 over theta, and that answer was 0. And that was about a 6-line proof. Yes, let's say it together. In chapter 2, it becomes 1 step, but we don't know section 2.2 yet. So what you do is you fiddle. You rewrite this as 1 minus cosine x over x times 1 minus cosine x. This, according to the theorem, will be a big fat 0. As x approaches 0, the cosine of 0 is 1. 1 minus 1 is 0. So, through creativeness, and if I could get my pen back, life would be great, but my pen is not calibrated good enough. The answer is 0. Okay, so there's some ideas of that section 1.2, but let's get really tacky. What is the limit as x approaches 5 of the greatest integer of x? The greatest integer is a step function. So as we go from 0 to 1, the greatest integer of x is 0. As we go from 1 to 2, this greatest integer is 1. As we go from 2 to 3, the greatest integer is 2. So that means if I come on down the road and I'm at 5, that from 5 to 6, the greatest integer will be up here at 5, but before 5, it would be down here at 4. So basically that means, and here we go again, pen trouble, the limit of the greatest integer of x as x approaches 5 from the left side would be 4, but the limit of the greatest integer of x as x approached 5 from the right side would be 5. So 5 to the left. I tell you, working with this calibrated pen, I heard someone tell me that if you wanted the pen calibrated, you simply just did not use this stylus. Okay, I'm trying to get it to do count 5 to the left here, and I'm having trouble. So, nothing I can do. You have to write fast and quick. So, the greatest integer is a step function. If you answer the question, you put D and E here, but from the left it's 4 and from the right it's 5 because it is truly a step function. You see it here as it travels from 0 to 1. 1 to the left is 0, 1 to the right is 1. 2 to the left side would be 1, 2 to the right side would be 2. So that's how greatest integer works. So remember, it's two cases. If it's not specified which side of C it's on, your answer is D and E. But never, 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 never do an always on every theoretical rule. Most likely it will be those answers. Let's carefully change the page again. It's working a little bit better. And let's study absolute value. What is the limit of the absolute value of x minus 4 over x minus 4 as x approaches 4? That's a thought. If you don't realize that absolute value has two cases, you're in trouble. The reason this is a graph is because absolute value has to always be positive. That's one of our theorems. So it's always on or above the x-axis. And if you remember, you had a curve where both sides were labeled with different equations. So the positive branch and the negative branch. So this problem alone, not saying which side I come from, I do not know what equation to put here. If I stick a 4 in here, I have division by 0. And I have just a question mark up here. So therefore, in that case, it's very simple to be a D and E. But you know, and I know, I'm not going to ask it like that. I'm going to ask you to consider to the right of 4, so that would change this problem to read as the limit as x approaches 4 to the right of x minus 4 over x minus 4, and that gives you an answer of 1. But if I change this problem to the limit as x approaches 4 to the left, then this absolute value would change to the negation of x minus 4. So my limit or my y value is negative 1. Now, I've touched on important points. What have I not touched on on 1.2. The application of proofs of linear functions. This definitely is class. So we've used up our 5 to 15 minutes. This is all that we can approach in here. So this will be for the next video. Recapping this evaluation of limits, I will title it Evaluation of Limits 1.2. Thank you for coming. Good night.